Lecture 2.2c, this is the second of the 3 lectures on end behavior. Last video we talked about how to prove that a function is an end behavior model. And it turned out that doing that proof requires a whole bunch of algebra. So now you're kind of wondering, well, why is it worth all the trouble to do that algebra? And so this video is going to talk about why should we care about end behavior models. So think about the meaning of this limit. The limit as x approaches positive infinity of f of x. By now you should be really comfortable interpreting this limit as a question, and the question is asking what happens to the output of the function as I input larger and larger x values. Well, the truth is there's kind of 4 possibilities, and I'm going to show you those 4 possibilities graphically. Take a look at these 4 functions. Each of these functions has different behavior. Of course, they're going to have different equations, but one of the things that makes them really different happens to be the end of the function. They're different, sure, at a lot of different points, but in particular, these 4 functions exhibit the 4 different possibilities when it comes to end behavior. Of course, you should remember that the limit as x approaches positive infinity is really talking about the right end of the function. So to evaluate this limit, I simply go to the edge of the function on the right-hand side, and I ask what's happening to the y values. For the red function, the y values are getting larger and larger and larger. So we would say that the end behavior of the red function is going to positive infinity. The y values increase forever. The blue function has y values that at some point seem to stop changing. The right end of the function achieves this horizontal shape. It's a horizontal asymptote. And we would say the right end behavior is constant. The y value at some point stops changing. So the answer to the limit would be just some sort of number. The green function, which is a sine function with a larger amplitude, is going up and down and up and down and up and down. So to answer this limit, what happens to the y values? Well, the y values continue to change, and we would say maybe they oscillate because they're going up and down. And so the answer to this limit would be dne. The end behavior here doesn't exist. There isn't a particular value that it approaches, and it also doesn't go to positive or negative infinity. The purple function has end behavior that goes to negative infinity, and you can see that the y values go down. So these are your 4 possibilities. Now, understanding them graphically is great, but the truth is a lot of calculus is about looking at equations and trying to predict what the graph's going to look like. So the question is, when we look at an equation, can you tell me immediately what's going to happen? Let's do 2 quick checks, and then we'll move on to some equations. Great, so you just answered this quick check in Edpuzzle, and hopefully you identified that the right end, which is the end where x goes to positive infinity, the y values have a horizontal asymptote, and it looks like it's at 0. So actually the right end behavior of this function is constant. And the left end, as we go the other direction, the function is going down really dramatically. So the left end behavior is negative infinity. This limit equals negative infinity. Let's try it backwards. If I tell you that the limit as x approaches infinity of f of x equals 7, and the limit as x approaches negative infinity of f of x is negative infinity, what do you expect to see on the graph? Perfect. So a constant end behavior, to me, I would expect to see a horizontal asymptote on the right-hand side. And negative infinity, I would expect this function to be going down dramatically on the left-hand side. So hopefully these 2 examples motivate you a little bit more to care about end behavior models. Limits at infinity help us predict the shape of the ends of the graph. So if we have a function that we don't know the shape of, calculating its limit at infinity could help us draw what the graph should look like. Take this limit as an example. Suppose we can't use technology and we need to figure out this limit. You can probably realize that this limit is basically saying what happens on the right end, but I have no idea what this graph looks like. It's some weird rational function. Furthermore, if I try to use my intuition, asking myself, well, what if I plug in really large numbers on the top and the bottom? The intuition fails because the top is going to get really, really large, and so is the bottom. So this is one of those infinity over infinity situations where just using your common sense isn't going to give us an answer. Luckily, there is a special fact, and it's a fact about n behavior models. If g of x is an n behavior model for f of x, then automatically the limit at infinity of f of x has to equal the limit at infinity of g of x. And this is great news because we already know an n behavior model for this function. We proved in the first video that g of x equals 3x to the fourth over 8x squared was an n behavior model. And we proved that by showing that the limit of f of x over g of x equals 1. Since we proved that, we can now use that fact to very simply evaluate this limit. The limit of f of x, which I have written right here, according to this very simple fact about n behavior models, now automatically equals the limit as x approaches infinity of g of x, which is 3x to the fourth over 8x squared. And this is because g of x is an n behavior model. Great news. Now, we go from a very complicated rational function to a very simple limit. This limit's easy to evaluate because we can just simplify algebraically. We now have the limit as x approaches infinity of 3x squared over 8. I just cancel it out in x squared. And this limit, I can confidently say, is going to equal positive infinity because this limit has very, very large numbers on the top and just a constant number on the bottom. This is the best way to calculate the limit of a rational function, but it does require that you've proven an n behavior model. Now, in case you're not convinced about this fact, because I don't want you just to take my word for it, grab a graphing calculator and graph both of these functions, f of x and g of x, in the same window. What do you notice? Here's my graph. This is f of x. As you see, it's a pretty complicated function. It has asymptotes and weird squiggly lines. And here is g of x, which is a pretty simple parabolic function. And in fact, if I get rid of these equations, we can start to take a closer look. For small numbers, the two functions are really quite different. But an n behavior model isn't really important because of the small numbers. It's important because of what happens farther out. So once we get past this small region right here, what you see is that the green line and the orange and the purple line are lining up really closely, in fact. And the farther we go towards infinity, the two functions actually merge. And as we go towards either positive or negative infinity, the functions eventually seem to be the same, even though they were a different way in here. That's the whole point. An n behavior model is a simpler function that once we get out to the extreme values, has the exact same y values, has the same behavior as our function, which is why we can use it to approximate. So, to recap, the algebraic idea is find an n behavior model and use the n behavior model to calculate the limit. Here are some for you to try. Pause the video, make sure that you pay attention to your limit properties for these middle ones, and when you press play, I'll show you the work and the answers. Great, so hopefully you found that the n behavior for the first one is that this limit equals 4. And here's how you should have shown your work. I used an n behavior model at this step and I explained that's what I did. And then I simplified the inside before taking away the limit. And then the limit, of course, equals 4 because that's a limit of a constant. To summarize this, I would say this function has a horizontal asymptote at y equals 4 on the right end of its graph. Pause and do B. The answer to B is that it actually goes to infinity. And here's what the work would have looked like, similar steps. To summarize, we would say this function's y values increase to infinity on the right end of the graph. Try C. C required a little bit more work. This is what my work would look like. Watch how I justify each step. So I started by splitting this limit into two limits, and I can do that because of the product rule. Now the product rule does rely on an assumption that both of these are defined, so we're going to keep going and just check that that assumption is true. After splitting it into two limits by the product rule, I used an end behavior model for the first limit and another for the second limit. And then I simplified algebraically inside, and finally ended up with two limits of constants, which gave me the limit equals -3. And to summarize what this means, it means that the function has a horizontal asymptote at y equals -3 on its right end. Try D. So the answer to D, it was probably tempting to do the same product rule thing, but I want to point something out here. If you used the product rule, it would look like this. And then if you took the next step, maybe using an end behavior model, you would find that this limit equals 0 and this limit equals infinity. And that should be a red flag right there. You cannot use the product rule when one of your limits equals infinity or does not exist. So actually, this is not allowed, and we're going to have to find some other way to evaluate this limit. Now, what you can do is you can actually just multiply the two fractions, and you get 3x squared over x squared minus 10x plus 21 on the bottom. I just FOILed the binomials. And now this function has an end behavior model. It's a pretty simple one, which simplifies to the limit as x approaches infinity of 3, which is 3. And that's a totally valid way to solve the limit. And we can summarize, in fact, this function has a horizontal asymptote at y equals 3 on its right side. Try the last one. Okay, so you probably saw that the last one we fail to have a way to solve this. This is a natural logarithm, and none of the strategies we used for end behavior models told us anything about natural logarithms. So that's actually going to be the next step. We need to know something about different function families, and this is where the last video will pick up.